This is the 20th episode of the Crystal Clear Electronics video series. It is about voltage regulators and current limiters with transistors. Chapter 20 was written by Viktor Vince. Our lead speaker today is Szabolcs Veréb, an electrical engineer. He is an assistant lecturer at the Budapest University of Technology. His main area of expertise is power electronics, but I believe he also teaches electronics at the university.
That's right. Power electronics is a very diverse field. Designing a power converter device requires both analog and digital electronics knowledge, and moreover, the development of embedded software is inevitable nowadays. Let me introduce you to the viewers as well. Next to me is Marcell Czirók, a senior student at Bolyai High School in Szombathely, who, if all goes well, will be an engineering student in Budapest next year. We might be meeting again in a few years.
I hope so. I can see this gadget in your hand. Can you tell us why you brought it into the studio today?
Of course. Well, it's a mass airflow sensor, and it was in my car.
And how are you going to go home with it?
Well, with this I don't think I can do that, because it's broken and my car has got a new one. But this way, I can show you what it is and how it works. It has a metal wire through which a constant current is driven by electronics. This metal wire is positioned in the tube here so that the air sucked in by the petrol engine can flow past it and cool the wire. Because of the flow of current heats this wire, if the air flows past it very quickly, it will have a lower temperature because it cools it, whereas if the air flows slowly, it will be warmer. It is good because the electronics can determine how much air can flow through it by measuring the resistance of the wire. After all, if air is flowing fast, the wire will be cooler, so its resistance will be smaller, so the electronics can determine the amount of air flowing through the tube. It can then send this information to the engine controller, which can use it to determine how much fuel to inject into the cylinders.
That's all well and good, but I still don't understand why you brought this in with you.
Well, yes, I haven't told you that yet, and that's where we get to the core of the video. Circuits need a stable supply voltage, even at varying load conditions, for correct operation. This is also true for this mass airflow sensor. The voltage of a car battery varies between around 9 volts and 14 volts with state of charge and load conditions. It'll be different if it is almost full and the alternator is charging, or if we have just tried to start our car several times on a cold morning to no avail. Therefore, the electric system of a car is designed in such a way that it works if the supply voltage is between 8 volts and 16 volts. Nobody would be happy if the loudness of the hi-fi system or the brightness of the headlights in their car would change with battery voltage. Of course, a resistor divider can easily create 5 volts from a 14 volt supply. The problem is, as soon as current starts to flow, the voltage decreases proportionally to the load. The other severe problem is that the output voltage is dependent on the input voltage. If the 14 volt becomes 9 volt on the input, on the output 5 volt will also decrease accordingly. The voltage produced by a resistor divider can only be considered constant if the input voltage is already stable and no load is applied to the output.
You could say that this is not a good solution for stabilizing the voltage. In order to create a constant output voltage, regardless of the input voltage, semiconductor components are required.
We have already learned about diodes in a previous chapter, and we also know that they can't withstand arbitrarily high reverse voltage. The reverse voltage, where a diode starts to conduct backwards, is called the reverse breakdown voltage. This voltage is usually high in regular diodes, 50 volts or even above, but there are special diodes called Zener-Diodes, where this voltage is precisely known and manufactured to be a certain voltage. These diodes are designed to work in the breakdown region. The breakdown voltage is indicated in the figure with U Zener. If the voltage across the diode is above this voltage value, the characteristics will be very steep. With a good approximation, the diode voltage does not change, only the current. Therefore, this region can be used very well for voltage stabilization. Connect the Zener-Diode in series with a resistor that limits its current, exactly as shown in this figure. If the input voltage is higher than the breakdown voltage of the Zener-Diode, the voltage drop on the diode will always be the breakdown voltage and the rest will drop on the resistor. If we apply a load to the output of the circuit, then current will flow through it, reducing the current flowing through the diode. The diode can only act as a voltage regulator as long as current is flowing through it, in other words, until the load on the circuit is not too high. If we model this simple unloaded circuit in a simulator and set the voltage of the voltage source to sweep from -4 volts to 16 volts, then the voltage at the cathode of the Zener-Diode will be as shown here. The horizontal axis shows the input voltage of the circuit, and the vertical axis shows the voltage of the Zener-Diode, so the output voltage of the circuit. It can be seen that below 0 volts, the diode behaves as a normal diode. From 0 volts to 6 volts, the output voltage equals the supply voltage, so there is no significant current flowing through the diode. If the supply voltage increases beyond 7 volts, we can see that the voltage is stable at around 6.2 volts. So the breakdown voltage of this diode is 6.2 volts.
We have built this circuit on a breadboard. It is powered by a lab power supply and the output voltage will be measured with a multimeter.
Well, let's do that! The setup here is like what you saw in an earlier video, where the multimeter is connected to this laptop, so you can see the multimeter screen on a bigger screen. You can also see that when I move it around here, that minus sign is flashing, so it is showing the voltage value in real time. Well, I'm going to measure the voltage across the diode, and Marcy is going to adjust the voltage of the lab supply. He's going to increase the voltage slowly. Wait a minute, Marcy, and let me put my multimeter here. Great. Now, we're supposed to see the voltage of the diode on the multimeter, and then slowly, as Marcy raises the voltage, you can see that until you get to this 6.2 volts, the voltage follows the input voltage, and you can see that it's now stopped, even though the lab supply is already at 10 volts. I don't think we should go any further to avoid a mishap here. At about 12.5 volts, we measure this 6.2, and we can see that we are above 6.2 volts by a few tenths of a volt, that is 10 millivolts, so it's a small error. We can say that this method of stabilizing the voltage works as described.
Zener diodes are manufactured with many different voltages, so it is easy to find one with the right parameters for your application and needs. This type of voltage regulation, where the regulating component is placed parallel with the load, is called shunt voltage regulation.
This brings us to the end of the first video. In the next one, we will look at the effect of load on this simple stabilization circuit.
Bye!